Reinforcement learning, it's just like me and you. We learn and adapt from experience, yes we do. StatQuest, bam. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about reinforcement learning and we're going to cover the essential concepts. This StatQuest is brought to you by the letters A, B, and C. A always, B, C curious. Always be curious. Imagine we were hungry and wanted to eat a snack and had to choose between going to Squatch's Fry Shack and Norm's Fry Hut. The problem is that we've never been to either place, so how do we decide which one to go to? Specifically, we'd like to know which place will do a better job giving us a satisfying order of fries. To solve this problem, we're going to use reinforcement learning. Reinforcement learning is a methodology that basically lets computers learn and adapt based on experience, and it's used in all kinds of situations. For example, reinforcement learning has been used to help computers become better at playing games like checkers and Go, and to help cars drive by themselves. And it's even been used to make ChatGPT sound more human when it responds to your prompts. That said, in this StatQuest, we're going to learn how it can help us decide where to eat fries. Note: what follows is just one example of how reinforcement learning can be done, and the purpose is to focus on the main ideas of how this method works. And, for now, we're going to ignore the copious amounts of terminology associated with this field. But don't worry, we'll dive into the terminology after this example. So, with that said, now let's see one way that reinforcement learning can help us decide where we should go eat fries. Since we've never been to either Squatch's Fry Shack or Norm's Fry Hut, we'll start with each place having an equal probability that we will go there. In other words, we'll start with the probability of picking Squatch's Fry Shack for a delicious snack, P Squatch, set to 0.5. And the probability of picking Norm's Fry Hut for a tasty treat, P Norm, set to 0.5. Now, to visualize how we will choose a restaurant, let's draw a line that is 0.5 units long to represent the probability of going to Squatch's. And then append to that another line that is 0.5 units long that represents the probability of going to Norm's. Combined, we have a line that goes from 0 to 1. Now, to decide which restaurant we want to visit, we pick a random number between 0 and 1. In this example, we randomly pick the number 0.7. And because 0.7 is in the region that represents Norm's Fry Hut, we go there. And when we go to Norm's, we are served a large order of fries. Bam! Getting served a satisfying order of fries at Norm's is awesome, but so far, we've only been there one time. And that means that we don't yet have a lot of confidence that most of the time we'll be served a satisfying order of fries at Norm's. And it's possible that Squatch's Fry Shack also serves satisfying orders of fries, so we still might want to try out Squatch's place. Because we were just served an order of delicious and satisfying fries at Norm's Fry Hut, but it was just our very first visit, and we're not sure if that will happen most of the time, it makes sense that we should increase the probability that we will visit Norm's Fry Hut in the future, but just by a little bit. So here's one way we can increase the probability that we will visit Norm's in the future, but just by a little bit. First, because these fries are so satisfying, on a scale from 0 to 1, we give them a fry score equal to 1. And then we can use this equation to calculate the new probability of visiting Norm's Fry Hut, new P Norm. This equation uses the existing probability that we will visit Norm's, P Norm, and combines it with the fry score that we assign to our order of fries, and a learning rate, which helps prevent changing the probability too much too soon. To calculate a new probability for visiting Norm's Fry Hut, new p-norm. So we plug in the current value for p-norm, 0.5, plug in the Fry score, 1, and then plug in a learning rate, which, in this example, we'll set to 0.1. Note, we'll show what happens when we have different learning rates in just a bit. For now, when we do the math, we get 0.5 plus 0.05, which is 0.55. And that means we increase the probability of going to Norm's Fry Hut to 0.55. We then calculate the new probability of visiting Squatch's Fry Shack, new p-squatch, as 1 minus new p-norm. So we plug in the value for new p-norm, 0.55, and we get 0.45. And that means we decrease the probability of going to Squatch's Fry Shack to 0.45. In other words, we increased the probability that we will visit Norm's again in the future just a little bit. And we decreased the probability we'll visit Squatch's just a little bit. Increasing the probability of visiting Norm's the next time we want to snack just a little bit makes sense, because even though we got a satisfying order of fries at Norm's, so far we've only been there one time. And it's possible that Norm's fries will not always be awesome, and it's also possible that Squatch's fries could be awesome, so we still want to have a chance to visit Squatch's. Bam. Now, before we move on and get hungry for another snack, let's reset the probabilities to what they were at the start, 0.5 for both Squatch and Norm. And talk about the learning rate. Learning rates control how big or little a change we will make to the probabilities each time we update them. For this equation, learning rates are set to values between 0 and 1. If we set the learning rate to 0, then the whole second term is equal to 0 and goes away. And we end up with the new p-norm equal to p-norm. In other words, when the learning rate is set to 0, we don't make any changes at all. In contrast, if we set the learning rate to 1, and then plug in the current value for p-norm, 0.5, and plug in the Fry score, 1, then we will end up setting new p-norm to 1. And that means that the next time we get hungry, we will go to Norm's without leaving any probability to visit Squatch's. And that's not really what we want to do right now, since we've never been to Squatch's. However, when we set the learning rate to something larger than 0 and less than 1, like 0.1, we end up setting new p-norm to 0.55, which is just a little larger than the original value for p-norm, 0.5. And that small change does a better job reflecting the satisfying order of fries we got from Norm's, while also preserving a chance that we'll visit Squatch's. Note, in practice, the learning rate is something that we usually set to some default value, like 0.1, and if it doesn't work, we test other values. Small bam. Understanding the purpose of the learning rate and updating the probabilities that we will visit Squatch's Fry Shack and Norm's Fry Hut is hungry work, so now it's time for another snack. Like before, we can draw lines to represent the probabilities that we will visit Squatch's Fry Shack or Norm's Fry Hut. But now the line for Squatch's is a little shorter, and the line for Norm's is a little longer. Next, we pick another random number between 0 and 1, and this time we get 0.2. And because 0.2 is in the region that represents Squatch's Fry Shack, we'll go there. And when we go to Squatch's, we get served an unsatisfyingly small order of fries. Wah wah. Hey Squatch, why are your fries so lame? I needed a snack too, so I ate some of them. Are you going to eat our fries every time? I don't know. I guess it depends on how hungry I am. Okay, just know that it's bad for business. Anyway, because Squatch's fries are unsatisfying, we give them a fry score equal to 0. And now we can use this equation to calculate a new probability for visiting Squatch's Fry Shack, new P Squatch. This equation is like the one we used earlier, but now we use P Squatch, the most recent probability for visiting Squatch's Fry Shack, instead of P norm. So we plug in the numbers using the same learning rate we used before, 0.1. And we get 0.41. So, because the fries at Squatch's were unsatisfying, we reduced the probability we will go there from 0.45 to 0.41. With the new probability for visiting Squatch's Fry Shack, new P Squatch, we can update our probability for visiting Norm's Fry Hut, new P Norm. And we increase the probability that we will visit Norm's from 0.55 to 0.59. Now when we draw out the probabilities, the line for Squatch's is a little shorter than before, and the line for Norm's is a little longer. So we pick another random number, and this time we get 0.1, so we go back to Squatch's. And again, when we go to Squatch's, the fries are lame. Double, wah wah. I couldn't help it. I was hungry. Anyway, like before, Squatch's fry score is equal to 0. And we use that to update the probability we'll visit Squatch's in the future to 0.37. Bloop, 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 bloop. Then we update the probability that we'll visit Norm's in the future to 0.63. Using this approach, we can continue to visit Norm's and Squatch's to update the probabilities we will go to each place. Most of the time, Norm gives us a satisfying order of fries. So the fry score for Norm's is usually 1. And, as a result, we usually increase the probability that we will visit Norm's. However, every now and then, Norm just can't resist and eats most of our fries. So the fry score is equal to 0. And we end up decreasing the probability that we will visit Norm's. And on the increasingly fewer occasions that we go to Squatch's, we usually get a lame order of fries. And, as a result, we reduce the probability that we will visit Squatch's even more. However, once in a blue moon, Squatch somehow resists eating our fries and we get a satisfying order. And we end up increasing the probability that we will go to Squatch's in the future. Anyway, now we just repeat these steps. We use the probabilities we will visit Squatch's and Norm's to determine where we will go to get fries. And then, based on how satisfying the fries were, we update the probabilities we will visit each place. After repeating those steps a bunch of times, the probability of going to Squatch's ends up hovering around 0.19. And the probability of going to Norm's ends up hovering around 0.81. In other words, every time we go out for fries, we change the probabilities, but after a while, those changes stay close to 0.19 for Squatch and 0.81 for Norm. And now we know that when we get hungry, most of the time we should go to Norm's, because Squatch gets hungry too often and eats our fries. Yum! Double bam! Now that we've seen an example of how reinforcement learning can work, it's time for a terminology alert. For starters, using reinforcement learning lingo, we would call Squatch's Fry Shack and Norm's Fry Hut the environment. The environment is something that we want to explore and can interact with. In this example, we explore and interact with the environment by visiting each place and ordering fries. And because we are the ones exploring the environment, we are called the agent. In this example, we, the agent, explore the environment by using the probabilities that we will visit squatches and norms. And these probabilities are called the policy. In this example, we use the policy in a very simple way. We simply pick a random number between 0 and 1, and if it lands in the area that represents norms, we go to norms. Otherwise, if the random number falls in an area that represents squatches, we go there. However, our policy could be more complicated by taking into account how many times we visited norms or squatches in the past week, or factor in how hungry we are. Lastly, the fry score, which we use to update the policy, is called the reward. In reinforcement learning, the goal is to modify the policy so that we can maximize the reward. And, in this example, that means updating the probabilities that we visit squatches and norms so that we maximize the delicious fries we are served. Note, in the example given here, most of the time, Norm gave us a great order of fries and the reward was relatively high. However, every now and then, Norm ate some of our fries and gave us a small serving, and the reward was low. So the reward can change and doesn't have to always be the same. To summarize, we, the agent, needed to explore the environment, which, in this example, means we needed to decide if we should visit squatches or norms. So we used the policy, the probabilities that we should visit each place, to help us decide where to go. And, depending on the order of fries, we either got a large reward or fry score, or a small reward. And because our goal is to maximize our reward, we update the policy so that we will visit the place that is more likely to give us a satisfying order of fries more frequently. Triple bam! Now it's time for some shameless self-promotion. If you want to review statistics, machine learning, and AI offline, check out the StatQuest PDF study guides and my books, the StatQuest Illustrated Guide to Machine Learning and the StatQuest Illustrated Guide to Neural Networks and AI at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying one or two of my original songs or a t-shirt or a hoodie, or just donate. The links are in the description below. All right, until next time, Quest on!